So within every bond, there is a particular energy. And so we can define the bond energy between two atoms as the average enthalpy change for breaking that bond between the two atoms in the gas phase. So it turns out that whenever we break a bond, we have to put energy in to break a bond. When new bonds are formed, that same amount of energy is released. So it turns out that if you can figure out all the bonds that have to be broken and then all the bonds that are reformed, you can find the total enthalpy of the reaction. It's approximately equal to the sum of the bond energies of the reactants, so the ones that you have to break apart, minus the sum of the bond energies of the products, which are the ones that are forming, the new bonds that are forming, which means energies released. So we can actually look up these values. So this is just, it's kind of similar to chapter 6, where we were finding the delta H's by using the products minus the reactants. This time we're just going to use bond energies. So you can find these bond energies in a table in chapter 9, and you can also find them, I think, at the back in an appendix at the back of the book. So here's how you sort of like a mileage chart, so how you read it. So if an HH bond breaks, it's 436 kilojoules. If a CH bond breaks, it's 413. If a CC bond breaks, it's 348. So you can see, you can read it. An NN bond is 163, but an NC bond is 393, and so you can read off the chart what kind of bonds that you're looking at. And then also notice that there are some multiple bonds, because a multiple bond's not exactly the same as two bonds, not double. So for example, two carbon single bonds, 348 times 2 would be almost 700, where you can see a CC double bond is 614. So it's not quite the same. So you have to, for a multiple bond, you need to look up those separately so you can see. So, and obviously for a test, these values would be given to you. All right, so the easiest way to look at this is to say, to look at this equation, delta All right, so let's look at an example. Let's estimate the delta H for the following reaction. And again, this is a little bit unusual because everything's in the gas phase, so it's not exactly the best data, and this is all the data that we have is everything in the gas phase. But we can get an idea for how much, what the delta H for this reaction is. Okay, so if you look at the reactants, you can figure out all the bonds that are broken. And note that we have 4 CH bonds and a CCl bond. And the products, so you could actually sum altogether the 4 CH bonds and 1 CCl bond. However, if you notice that actually 3 out of the 4 CH bonds are still in the product, so actually only 1 CH bond is broken and 1 CCl bond is formed, and a CL-Cl bond is broken, and then an HCl bond is formed. So again, 1 CCl bond is formed and 1 HCl bond is formed. In a second, I'll talk about if you can't see that, it's okay to just go ahead and totally break every bond and then reform every bond. So in this case, if you had said, all right, we're going to break through 4 CH bonds and a CCl bond, and then we're going to form 3 CH bonds, a CCl bond, and an HCl bond. You can see that the 3 CH bonds that were first broken and then reformed will just cancel each other out. So if you get yourself confused, just break every single bond and form every single bond, and you're okay. Or in this case, you can see, all right, 3 out of the 4 CH bonds stay in place and only 1 breaks. And so either way will work. Okay, so if we refer to the bond energies, we can look them up and then we just add together. So here we can see delta H is the bond energy for a CH bond plus the bond energy for a CCl bond. And then we're going to subtract from that the total of the bond energy of a CCl bond plus the bond energy of an HCl bond. So a CH bond is 413, a CCl bond 242, so that sum will equal 655. And then a CCl bond is 328, an HCl bond is 431. And so if we add those together, we get 759. And so 655 minus 759 gives us a delta H of negative 104 kilojoules. So this is an exothermic equation, and we found the delta H by doing that. So I hope that makes sense. All right, so let's do one more example. Find the delta H for the following reaction by using the bond energies found on table 9.5. I drew this one out so that you can see the different bonds that are there. So if by inspection we can see that, and in this case we have to be a little bit careful because remember a single bond is not the same as two double bond. A double bond is not the same as 2 single bonds. So what we have to do here is what do we have to break? We're going to have to break a CC double bond and we're going to have to break an HH bond. Okay, so a CC double bond and an HH bond. What's going to have to be formed on the other side? Well, we're going to have to reform that CC bond. It'll be a CC single bond. Then we have one CH bond to one of the carbons and another CH bond to the other carbon. So we have one CC bond that's forming and 2 CH bonds that are forming. So if we look up those values, we can see that the bonds broken are the CC double bond and the HH single bond, 614 kilojoules. Remember to look at the bottom of that chart, plus 436 kilojoules. So that's a total of 1050. And then we have 2 CH bonds being formed. So 2 times 413, and then 1 CC single bond, 348. If we add that together, we get 1174. And so 1050 minus 1174 gives us negative 124 kilojoules per mole. So again, you just have to go through and by inspection, find the bonds that are being broken and the bonds that are being formed. And like I said, if you get yourself confused, just break every single bond and then reform every single bond. So in that case, there were 4 CH bonds that didn't get touched. If you wanted to break them at the beginning and then reform them all at the end, the numbers would work out just the same. Okay, so the very last thing that we're going to talk about in this unit is ionic bonds. So actually it's the first section of the chapter in your book, but I put it till the end, partly schedule-wise for doing the lab, which may or may not affect you if you're watching this. But anyway, we're now going to just be switching and looking at the first section of chapter 9, so ionic bonds. Remember that an ionic bond is a chemical bond formed by the attraction between a positive ion and a negative ion, or positive ions and negative ions. So we know that at some point there had to have been a transfer of electrons from one atom, generally speaking a metal. Metals are the ones that give up atoms and become positive, and then nonmetals gain electrons to become negative. So ionic compounds are generally metal and nonmetal, or a metal and a polyatomic ion. The number of electrons lost or gained is determined by its need to be isoelectronic with a noble gas, or in other words, to have a full octet. In general, we know hydrogen only needs 1 to be like helium, but most of these atoms will gain or lose electrons to try to be just like a noble gas. Some of the Some of the transition metals will not exactly do that, but they try to become more stable. So maybe a half-filled D subshell, or a half-filled S and a full-filled D subshell, something like that. All right, so again, it's because noble gas configurations are very stable, and that's why they want to be like noble gases. So atoms that lose electrons become positive, and we call those cations, which you should already know that from earlier in the chapter 4, I think. So here's an example, and we can see the electron configuration, which shows how it's working. So sodium, which has a neon shell core plus one 3s electron. If it loses that one electron, then it has just the neon core, and so it's isoelectronic with neon, and it loses one electron. So that's how we represent it. Atoms that gain electrons become negative, and those are called anions. And so we can see again with the noble gas configuration, for example, chlorine, which is really one short of having a full shell. If it gains that one electron, becomes a neon shell plus 3s2 3p6, or actually, in other words, just like argon, isoelectronic with argon. So you could write it just argon in brackets. We can draw what's happening to the electrons by showing the transfer. So what happens when a sodium atom and a chlorine atom react together? Sodium will give up the electron, chlorine will gain the electron, and we have the two ions. So actually that transfer has a particular energy involved with it. But then there's also energy involved with the two ions now being attracted to each other. So these are two different things that happen. So the sodium and the chloride are now attracted to each other, and there's another, like I said, another energy that goes along with that. When those two ions are attracted to each other, that is called an ionic bond. We can actually draw Lewis electron dot symbols. We've already done a little bit of that earlier in the chapter, but we can draw the symbols for when atoms have gained or lost electrons. So we know that the valence electrons are just equal to its group number. So actually, this is the same slide that we saw earlier in the chapter. We're just repeating it to remind you. So the group number indicates the number of valence electrons, and we can draw how many electrons there are surrounding the atom, up to 8. But then we can also illustrate what's happening when an electron is being transferred. So again, let's look at magnesium to fluorine. So magnesium has 2 electrons to give up, but fluorine only has 1 vacancy. So if you look here, magnesium has those 2 electrons. It can't give both of them to one fluorine because fluorine only wants 1 more. So if you take 2 fluorines, then magnesium can give 1 electron to each of those fluorines. Magnesium has to give up 2 because it wants to, again, be isoelectronic with neon. So it has to give up 2, but it has to give them up to 2 different elements, to 2 different fluorine atoms. And so when they do, each fluorine becomes negative, and magnesium becomes positive too, and then of course they're attracted to each other. So that's why the formula is MgF2, which of course hopefully you already knew that back from chapter 4 when we kind of had to do it without explaining why it happened, but now you can kind of see what's happening a little more particularly in figures. Okay, so magnesium will form MgF2 because 1 electron is given to each of the fluorines. Okay, so we kind of fib a little bit because we're always saying, well, sodium really wants to get rid of an electron and chlorine really wants to gain an electron, but the actual transfer of that electron from a sodium atom to a chlorine atom actually requires energy. You have to put some energy in to make that transfer happen. 147 kilojoules per mole has to be put in. However, now once you've got these ions formed, the fact that they're going to be attracted to each other, as they're attracted to each other, they release 493 kilojoules of energy. And so you can see overall there's still a release of energy, so it is much more stable in the end. You just have to put that, you have to have enough energy, you have to have a little bit of energy to put in to get the process going. And then it turns out that once those ions come together and solidify, and another 293 kilojoules of energy is released. So even though you have to put a little bit, 147 in, you get almost 800 back out. So what is that? If you kind of approximate 800 minus 150 is about 650 overall out. So it's definitely worth the little bit of energy that you need to put in. So this extra energy released when these charged ions come together and then form a solid is called lattice energy. So the lattice energy, actually, the lattice energy would be how much is stored in the lattice. It's released as this lattice is formed, and then to break the lattice up, you have to put that much energy in. So the energy released when the gaseous ions form a solid is called, is released, and that is the negative of the lattice energy. Picture shows a little bit. So if you have 1 mole of sodium atoms and 1 mole of chlorine atoms, the first thing you have to do, you can see step 1 is you have to put 147 kilojoules in to form the sodium ion and the chloride ion. In step 2A, as those ions form a pair where they're attracted to each other, 493 kilojoules of energy is released. So that's why it's negative. And then as those ion pairs solidify, another 293 kilojoules is released. So the lattice energy together is 786 kilojoules. The negative of the lattice energy would be considered 786 kilojoules. That's how much is actually stored in the lattice that was released during this process. And you would have to put that much energy back in to break those bonds. But you can see overall there was a net energy released of 639 kilojoules. So the actual transfer requires energy, but then everything else releases energy. So it is very energetically favorable. So just a few other things to tie up. As metals lose their electrons to form a noble gas configuration, we know that electrons are lost or gained. Actually, for cations, we know the electrons are lost. So for example, magnesium loses 2 electrons, and so we sort of showed this earlier, but we can write that loss like this. So magnesium metal becomes magnesium 2+ and loses 2 electrons. And you can see the noble gas configuration. So magnesium has 2 3s electrons, but then once they're gone, it's got that same core as a neon, so it's isoelectronic with neon. Okay, so the transition metals don't work exactly like the other ones. They can't ever actually form a noble gas configuration, so they actually form kind of a pseudo-normal noble gas configuration. So they don't always lose their order in the reverse of how they gained those electrons, or in other words, you don't remove them in the same order that you filled them. So generally when you're trying to figure out the electron configuration for a transition metal, the first thing you want to do is remove the s electrons from that row. So like if it was in the 3D, if there was a transition metal in the 3D subshell, you would first remove the 4s electrons. And then if you need more, lose those d electrons, like the 3d electrons. So for example, iron can form 2 different ions. It can be a +2 ion, so it forms this pseudo-noble gas. So you can see Fe ends with 4s2 3d6. So the first 2 electrons that need to be removed, if you're just removing 2, remove the 4s electrons. So it gives the noble gas argon 3d6. If our iron can also make a +2 ion, so again, now you would first remove the 4s2 electrons, and then since we need to remove 1 more electron to get a +3, we would lose the one more 3d electron. So the noble gas configuration for, or the electron configuration for iron 3 plus would be argon 3d5. All right, just again, a few more things to tie up. An ionic radius, we already talked about a molecular radii. The ionic radii, or radius for single, is a measure of the size of the region around the nucleus. So basically from the center of the atom until the farthest electrons, the outer shell electrons. And so if you remember, atoms generally increase in size as you go down a column. And for the same reason, ionic radii will also increase as you go down a column because you're adding additional shells. So ionic radii increase as you go down a column. However, things get a little bit more complicated if you go across a period. So actually, cations will decrease in radius. So if you go, say, from potassium to calcium, calcium will be a little bit smaller. If you remember the atoms radii decreases as you go all the way across. So if you're not talking about the ions, if you're talking about the atomic radii. So calcium would be smaller than potassium, or magnesium would be smaller than sodium. And then the same is true for the cation. So a magnesium ion is smaller than a sodium ion. A calcium ion is a little bit smaller than a potassium ion, and that's because they have the same number of electrons, but they have more protons in the center, so they're being pulled in a little bit more. But if you're talking about ions and you keep going across the column, once you get to the anions, the negative ions, remember that we're adding them, and so all of a sudden the radii will jump up because we're filling up that higher shell now, and so there's an abrupt increase in radius, but then as you keep going to the right, the negative ions, the ions will decrease. So like potassium and then calcium will be a little bit smaller, and then the transition metals, and then when you get to arsenic, which will be negative, it'll jump in size, but then selenium will be a little smaller, and then bromine will be a little smaller, and krypton will be a smaller. So also, if you're trying to compare a neutral atom to its ion, you can see that positive ions, because they're losing their whole outer shell of electrons, it becomes smaller. So positive ions are smaller than the neutral atom. And actually, you might think that the negative ion would stay the same size, but because there's more electrons, the pull is a little bit looser, and so the ion does become a little bit bigger. So negative ions become a little bit bigger. Now, within an isoelectronic group of ions, how can you decide which one has the largest ionic radii? Well, what you need to do is look at the number of protons. So the one with the greatest number of protons will be the smallest. So for example, if we look at these here, calcium 2 plus, calcium, the atom has 20 protons and 20 electrons. So if it loses those 2 electrons, it has 18. Potassium has 19 protons and electrons, loses 1 to become isoelectronic with argon, also has 18 electrons. Chlorine gains 1 electron to become like argon, and sulfur will gain 2 electrons. But so notice they all have 18 electrons. They all have the same number of electrons, but a different number of protons, and so their ionic radii will be different. In fact, because calcium has the most number of protons, it will pull the hardest on those electrons, and so calcium will be the smallest. Potassium will be a little bigger. Argon a little bigger than that, chlorine a little bigger, and then sulfur will be the biggest because those electrons are being pulled the least because there's fewer protons in the nucleus. Okay, so you can see that. All right, so what should you be able to do in this chapter? Well, you should be able to use Lewis symbols to represent ionic bond formation. So sort of showing like sodium with 1 electron, chlorine missing an electron, and then showing the transfer of the electron over, and then finally showing the ions on the other side. I think a few slides back, you'll see that we did that with magnesium and fluorine. You should be able to write the electron configurations of ions. Remember that in general, you just have to take away the last electrons that you added. Or if you're adding electrons to make it negative, you just add electrons to fill up the rest of that row. However, if you have the transition metals, remember that you have to lose the s electrons first before you lose any d electrons. So we went through the example of iron. Iron plus 2 would lose the two 4s electrons, and then iron plus 3 would also lose one of the 3d electrons. You should be able to use periodic trends to figure out the relative ionic radii across a chart, or across the chart, or up and down, or if it's positive versus neutral, or isoelectronic, again, as we just saw. You should be able to tell if a bond is polar or nonpolar by using electronegativities or even ionic. You should be able to write Lewis formulas for simple molecules. Oh, also, and ions, Lewis formulas for molecules and ions. Don't forget that the ions, if it's negative, you have to add that many electrons to get the valence, total valence. Subtract some if it's positive. And then you should also be able to write the resonance structure. So for example, if you need to make a double bond to an oxygen, but there happen to be 3 oxygens there, then you need to write the structure 3 different times with the double bond going to each of the oxygen. So that's called resonance. You should be able to relate bond order and bond length. Bond order just tells me how many bonds there are. So first order is a single bond, second order is a double bond, third order is a triple bond. And then remember that bond length is inversely related. So a single bond is the longest, a double bond is a little shorter, and a triple bond is even shorter. You should be able to estimate delta H's from the bond energies. Remember, we sum up all the bonds broken and then subtract the sum of all the bonds formed. You should be able to predict molecular geometry. So not just, you should be able to predict by the number of regions. So 2 is linear, 3 is trigonal planar, 4 is tetrahedral, 5 is trigonal bipyramidal, and then 6 is octahedral. But then you should also be able to drill down and tell the molecular, those are the structural geometries, and then the molecular geometries where, for example, if there's 4 regions and 3 are bonding, that would be a trigonal pyramid, or 5 regions but 4 bonding would be seesaw. So be able to predict those. And then also be able to tell if a molecule is polar or nonpolar. So you can find out if there's any polar bonds, and then look at the dipole, how they're, if they're all the same and they all cancel each other out, then the molecule will be nonpolar. And so be able to tell if a molecule is polar or nonpolar.